Good evening, gentlemen. My name is Mastorocostas. I'm professor at the Department of Informatics and Computer Engineering at the University of West Attica in Athens, Greece. And my team is proposing deep learning methods for electric load forecasting. During the last 30 years, computational intelligence and machine learning methods have dominated the area of electric load forecasting. And the first attempts concerned static feed-forward artificial neural networks, followed by fuzzy neurofuzzy systems in the early 1990s. Next, support vector machines and extreme learning followed with some very interesting, very effective methods, while evolutionary computation and some genetic algorithm-based forecasters were applied to the problem of the Greek power systems as well during the late 90s. In the 21st century, and after the revolution of deep learning, a lot of deep learning based methods were invented, including convolutional neural networks, recurrent neural networks, long short-term memories, and gated recurrent units. And they came up with very significant contributions that have been made. So, in this perspective, the aim of our work is to propose two models, a long short-term memory one and a gated recurrent unit-based model for short-term load forecasting for a particular power system, the Greek power system, where hourly-based predictions are extracted for the whole year. So these models have a very reduced input vector, which and they exploit the internal dynamics of the recurrent units in order to identify the temporal relations of the load time series. So let's take a quick look on the LSTM and the GRU models. First, the LSTM network. So this is the basic unit of such a network. The LSTM networks overcome the vanishing gradients issue, which is a very common problem when dynamics exist, and a big failing of the typical recurrent neural networks. The scope of the memory cell, which is the basis of those networks, is to store information and allows the information to persist over long periods of time. The information enters to the memory cell via the input gate, one of the three gates, which is implemented either by the sigmoid function or the hyperbolic tangent. I prefer the sigmoid function, and determines the information that will be stored in the memory cell based on the current input and the value of the hidden state at the previous time step. The second gate is the forget gate, which is complementary to the input gate, since it determines the amount of information that will not be taken into consideration at the memory cell. And the final gate is the output gate, which determines the information that is read by the memory cell. So both the forget gate and the output gate are implemented either by sigmoid or hyperbolic tangent functions. So at each time step, the outputs of the three gates are extracted, and the memory cell and the hidden state are calculated, are updated. Next, the value of the hidden state becomes the input of the next unit in the network for the next time step. The GRU model is a modification of the LSTM model. In fact, it is a simplification of the model. So it bears great resemblance to LSTM memory cell. It lacks just one gate. The structural unit is either the sigmoid or the hyperbolic tangent function as well. And this configuration has the advantage of containing fewer parameters, usually 25% less parameters, and lower, of course, computational burden. Despite their simpler structure, GRU networks perform similarly to LSTM counterparts in a variety of problems, including STLF, as we shall see in the sequel. So, let's start with a particular problem in hand, and with the problem statement. So the task is to perform forecasting of the next day's hourly loads of the Greek interconnected power system. Data are publicly available in the internet, and we have a very important task to perform when we want to model something. And this task is the selection of the input vector. So the input vector generally should satisfy two conflicting conditions. On one hand, it should be very informative as possible. So in this case, usually it leads to an excessive size. On the other hand, the number of input variables should be kept to a minimum in order to attain reduced complexity and avoid problems linked to the curse of dimensionality. So these conflicting conditions are very difficult to be satisfied at the same time. So in our case, we propose a single model that is built to provide load predictions for all kinds of days, including weekdays, weekends, holidays, and for all seasons. The input is the actual load at the same hour of the previous day, and the task of the recurrent call unit is to model the intrinsic time dependencies on past loads. So, in the present work, climate variables like temperatures are not considered, and therefore, no preprocessing stage is required. Since we want to check whether such a network is able to identify the lower time series without exogenous inputs. We use two error measures. Our primary error measure is the mean average percentage error. The average percentage error uh, is uh, the average percentage difference between hourly loads and the daily peak. And the secondary measure is the well-known, the popular root mean squared error, which measures the discrepancy between the actual datum and the forecast output. So the average percentage error uh, measures the difference between the load, the output of the models, and the daily peak, not the load at each hour. So first of all, we have the data set. We used 3 years as the training set and 1 year as the testing set. We split it the available data set to a ratio of 75 to 25%. And those data were provided, as I said before, by the Greek independent power transmission operator. At the first phase, as in every data mining problem, is the data integration phase, where the missing and irregular values should be substituted, and a normalization should be taken place, such that the data should be ready for the LSTM and the GRU networks. The data integration phase uh, uh, operated as follows. Wherever missing or irregular values occurred, they were filled by linear interpolation. And when we have consecutive missing values, a cubic spline interpolation was applied. Then data were normalized to the interval 0 to 1 by use of the common min-max scalar function. So in order to highlight the characteristics of the particular data, and the time series as well. This figure hosts the box plots for the training data set. And we can see it is obvious that there exists a cyclical behavior since there is seasonality. Moreover, as we can see, there is a pattern that is repeated every, let's say, 9,000 samples and is easily distinguishable since a whole year consists of 8,760 hours. And this pattern is repeated, as I said, approximately every 9,000 samples. So during winter and during summer, we can see that there are some peaks, while during spring and autumn, there are troughs. So these two seasons can be distinguished by the peaks. Both pairs of seasons can be distinguished by peaks and troughs, respectively. In this slide, we can see the seasonality for the training set, and of course the testing set in the picture below, it can be easily observed that there is an upward trend in the training set for the second and the third years. And this trend goes on for the fourth year, which is the testing set. Moreover, as far as seasonality is concerned, the peaks and the troughs, which indicate the summer and winter and pair and the autumn and spring pair, respectively, are clearly identified. So the lower picture, as I said, presents the testing set. We see the trend, we see the troughs and the peaks. So it's a set that follows the same lines as the training set. So let us proceed to the experimental results. We try to have an extensive experimental analysis with a series of structural and learning parameter sets, and we selected 8 models, 4 from each category, and the results, their parameters and the results are hosted in the table on the slide. So each time training lasted for 1,000 iterations, 10 trials were executed per case and the results were averaged. And as we can find in literature, a maximum average percentile error or threshold for an accurate prediction is 2%. So values below 2% give quite accurate predictions. As we can see from the results, all 8 models provide quite good predictions and some very good predictions. So both LSTM and GRU operate very efficiently, despite the fact that no climate variables or lagged values of loads are included in the parameter set. This behavior can be attributed obviously to the recurrent nature of the cells, which is proved effective, according to the results, to track the time series dynamics. The third and the fourth models from each category provide the best results. And we can say that the GRU networks operate very efficiently while demanding 3/4 of the parameters that an LSTM network demands. For example, the models at the fourth column require 482,000 for the LSTM model and 363,000 for the GRU model. As far as the best models are concerned, the third column, the GRU has approximately 2.2 million parameters, while the LSTM has approximately 3 million parameters. So there is a reduction of 25% that takes place, while the respective reduction in training is about 54 to 59%. Accordingly, the best GRU model will be used in the sequel, the next slides, in order to be assessed and to further investigate the behavior of deep learning-based forecasting. So we proceed with the GRU model from the third column, and the absolute error for the tested data set attains a yearly average of 59 megawatts, while the standard deviation is approximately 57 to 58 megawatts, which leads to the conclusion that most of the 8,700 and more hours of the year that consist of the testing set, the prediction error is less than 117 megawatts, leading the conclusion that the forecaster provides quite robust predictions. In the upper table, the seasonal characteristic results are reported. Let me remind you that we used one model for the whole year. We didn't use 4 models for one for each season, etc., or different models for the weekend and the weekdays or the holidays, in an attempt to investigate whether these recurrent models are able to identify the internal time dependencies. So, even though prediction for the whole year is carried out with the use of a single model, GRU Forecaster predicts well below 2% in all seasons, while summer is the easiest season to predict, and the rest three seasons exhibit similar root mean square error and average percentage errors. The remark I made a couple of minutes ago about robustness is supported by the absolute error duration curve, which is hosted in the table below. What is this curve? This curve presents the percentage of hours during the training year, the testing year, excuse me, in which the absolute prediction error is greater than the thresholds of the first row. So, as you can see, according to the results shown, GRU is quite an effective forecaster and a robust one, since for more than 83% and 93% of the time, the forecast error is less than 100 and 200 megawatts, respectively. While in the case of big errors, more than 500 megawatts, these errors take place only 9 times in 8,760 times. So the error is less than 0.10%. In the sequel, we present some graphs for the weekdays and the weekends for all seasons. And in these charts, the actual loads are painted in blue, while the errors of the forecaster are painted in red. In this slide, you can see the weekdays. In the next slide, we can see the Sundays. And let's comment on these graphs. First of all, it is concluded that the first minimum, the morning and the evening peaks, share a common time pattern for the working days of all seasons. On the contrary, the evening minimum stands more discrete in the working days of summer and autumn. The next conclusion is that the load curve of Sundays is quite different from the rest of the days, which is obviously an obvious conclusion, and is very reasonable, since there are different social and working conditions on Sundays. The third conclusion that is drawn is that even though both the seasonal patterns and the day types have some differences, the proposed model, in this case the GRU model, identifies and tracks the actual load curves accurately, including the appearances of peaks and minimum loads. Obviously, Sundays are more difficult to predict due to lower loads and different social activities, as I said before. Despite this fact, the single limb forecaster tracks quite effectively the transition from weekdays to weekends and vice versa. However, there are some limitations in our model since we don't use past loads or climate variables. Past loads in these two cases. We have in Greece, we have two highly irregular days. We have the Orthodox Easter Day and the Assumption Day, which is the August 15th. The Orthodox Easter Day is always on Sunday. So we can see on the left that the lower curves, the lower curves are plotted, that during these days, no morning peaks exist, and the load demand keeps decreasing until 3 p.m. approximately, or 4 p.m. for the Assumption Day. And additionally, during Easter, the lower curve attains significantly reduced values compared either to the same hour the previous day, the Saturday, or the previous Sunday. As a result, large errors occur. This irregular evolution of the electrical load is attributed to the nature of the particular day in Greece, where industrial activity is a minimum. A similar behavior takes place on August 15th, the Assumption Day, where GRU forecaster doesn't perform accurately until 4 o'clock, while it performs very accurately after 4 o'clock in the evening. Even though it tracks the dynamics, big errors occur, and a similar explanation is given. Since on August 15, which is a summer day as well, most Greek people are on summer vacations and they stay outdoors during morning and noon hours. Nevertheless, when the load curve returns to its usual pattern around 4 p.m., the forecaster's performance is greatly improved. So we can say that in conclusion, the single input model is not able to identify these irregular profiles and requires some extra trimming. It requires, for example, additional information regarding the nature of these days. So, concludingly, we could say that two deep learning models for short-term power demand forecasting for the Greek power system have been proposed. They have recurrent structure, so this structure enables them to effectively track the electric load curve. Next, the key feature of the proposed forecaster and the novelty, I could say, is a single input vector, a very simple input vector that doesn't include climate and temperature variables and consists merely of the most recent past load value. The experimental analysis has shown that both forecasters generally produce accurate predictions for the whole year, and it has been concluded that these models have limitations when highly irregular days occur and a significantly different load evolution appears compared to those of previous days. So we don't have enough information to perform an efficient prediction for these days. Therefore, an immediate future step is the introduction of an additional input that provides information about the type of the day. And let me add something stem from the fact that the previous presenter has said about particle swarm optimization. It is our intention, the intention of the team, to come up with the implementation of evolutionary computation-based algorithms, either PSO or ant colony optimization. Thank you for your attention, and I'm ready for some questions. We studied a single layer, obviously, and the results were about 1.47% for the average percentage error. So it was an obvious step to come with two layers, and the average percentage error ameliorated very much. No, because the number of parameters would be very high. These are yes. The RMSC is in megawatts. They are megawatts. Yes. I could add one more thing that yesterday, due to the weather conditions, the peak for the Greek power system was above 9,000 megawatts. Okay. Information criterion. No, we didn't apply this criterion in this work, but it's a good point. Yes. I myself use it more than 25 years in other modeling problems. So, thank you again for your attention.
Thank you very much. So we conclude with the other paper of Professor Anastasios.
Κλείνω το